Hello everyone. So let's see some questions from GATE exam in metal casting process. So the first question you can see a cast product of a particular materials has the dimensions of 75 mm cross 125 mm cross 20 mm. So let's see if I write complete solution of this question, then you can see here a cast product whose size is given, correct? So let's say this is a product which is made by casting process and its dimension is given, that is 75 mm by 125 mm by 20 mm. The total solidification time for the cast product is found to be the solidification time for the casting means cast product is 2 minutes. As a calculated using Chvorinov's rules having the index n is equal to 2. And if I write Chvorinov's equations, so simply it can be written as the solidification time is equal to k times of V by Sa whole to the power n, and here n is 2, so it can be written as k times of V by Sa whole square, where V is the volume of the casting and Sa is the surface finish of the, surface area of the casting. Yes or no? If the under the identical casting condition the cast product shape is to be changed to be cylindrical, let's say this is cylindrical casting, and whose diameter and height is remained same. Diameter and height, this is equal to 50 mm. So what is the solidification time of this cylindrical casting is? We need to calculate this. So from this, as you see, the material of both the materials, both the casting is remains same. So this constant, solidification constant is remains same. So simply if I write solidification time of cylindrical casting over the solidification time of rectangular casting, solidification time of rectangular casting, let's say this is rectangular casting, let's say this is R. So this is nothing but it can be written as V by SA of cylindrical casting over V by SA of rectangular casting, correct? So if I write V by SA, now you can see here the diameter and height is remain same, and when you write V by SA of cylinder, V by SA of cylinder, when its diameter and height is remain same. So if you write here the volume, that is pi r, volume of the cylinder is nothing but this is pi r square into h over the surface area is nothing but this is pi r square, or simply if you write in the form of diameter, so it can be written as pi by 4 d square into h, and here the diameter and it is remain same, and this is pi by 4 d square, and this is 2 plus pi dh, correct? And now if you simplify this expression and while putting the diameter is equal to height, so simply we can write V by SA of cylindrical casting, this gives us d by 6, and here since here we assume capital D, so it can be written as d by 6. So simply here I am writing ds solidification time of cylindrical casting over solidification time of rectangular casting. This is equals to, this is d by 6 over, and for rectangular casting simply we can write L B into H. This is volume over LB plus BH plus LH and 2 times. Correct? So this is surface area. So now if we put these values on this expression, so simply here we get d by 6, diameter is given, that is 50 mm. So it can be written as 50 by 6. And if I write this, so the if I talk about the dimension, then you can see 75 by 125 by 20. So this is 75 into 125 into 20 over 75 into 125 plus 125 into 20 plus 20 into 75, and this is 2 times. Correct? And after, when you simplify this expression, then the solidification time of cylindrical casting is nothing but this is 2 times of this factor. 2 times of this factor. Is it clear? 2 times of this factor. And after simplifying this, here we get 2.83 minute. 2.83 minute. This is the right answer. So you just calculate and solve it. Yes or no? So from this, here we get this answer. Is it clear? So this is the procedure for solving this kind of question. Yes or no? Let's see another question. Okay, so you can see here, a true centrifugal casting operation needs to be performed horizontally to make copper tube of section with outer diameter. Yes, here we have outer and inner diameter. This is the hollow pipe. And if I write its outer diameter, then this is 250 mm. Similarly, if I write in internal diameter, then it will be 230 mm. Correct? The value of acceleration due to gravity, G, is also given here. That is 10 meter per second square. If G factor, that is the ratio of centrifugal force to weight, is equal to 60, and this is nothing but this is centrifugal force over weight of the casting is equal to 60, the rotational speed. So here we need to find out rotational speed in RPM. Correct? So how to solve this? So simply, as you know that the G factor, which is equal to Fc by W, and where Fc is nothing but this is mr omega square over, and the weight of the casting is mg. Yes or no? So from this, mass is cancelled out with this, and now you can see, what about radius? So simply here we can write, and this is equal to 60. Correct? So omega square is nothing but it can be written as 60 into G over R. Yes or no? 60 into G over R. Correct? 60 into G over R. So you can see, for calculate omega, here I am assuming the outer diameter, outer radius. So simply you get 60 into G is given here. G is given here, that is 10 over R naught, that is D naught by 2. This is equal to 250 by 2. Correct? So after calculating this, and if you remove this, so simply here we get omega equals to square root of this value, 60 into 10 over 250 by 2, that is 125 into, this is omega. Yes or no? This is omega, and after getting omega, we need actually n. So n is nothing but, sorry, omega is nothing but you can see here. So as you know that angular speed omega is equal to 2 pi n. Omega is equal to 2 pi n, and if you divide with 60, then here we get n in minute. Correct? So the n can be written as 60 times of omega over 2 pi. So let's see, if we put this value on this expression, sorry, if we put this omega value on this expression, so simply here we get n is equal to 60 into square root of 60 into 10 over 125 over 2 pi. Yes or no? And after simplifying this, And one more thing, you can see the G is given in 10 meter per second square. So we need to put this radius in meter. So instead of writing 250 by 2, can I write this is 0.25, 0.25 by 2, correct? Or simply you can say from this is 0.125. So make sure unit, correct unit. This is 0.125. So after simplifying this, here we get 662 RPM. 662 RPM. So like this, you can easily solve this problem. Yes or no? So let's see another problem. This is very simple problem, correct? Next, you can see here. Okay. So a mold cavity of 1200 centimeter cube. The volume of mold cavity is given here, that is 1200 centimeter cube, has to be filled through a sprue of 10 centimeter length of the sprue means HS is given here 10 centimeter, feeding a horizontal runner. The cross section area of the base of the sprue, cross section area of the base of the sprue means if I draw a sprue, then this is the base area, this is the base area, and this is the top area, correct? So let's say if this is point 1 and this is point 2, so can I say this is A2, and here A2 is given, that is 2 centimeter square. Considering acceleration due to gravity, that is G is given 9.81 meter per second square. Neglecting friction loss due to molten metal flow, neglecting the friction losses due to the molten metal flow, the time taken to fill the mold cavity in second. So we need to calculate filling time. We need to calculate filling time or pouring time in second. Correct? So if I assume this is a top gate, if I assume this is the top gate, then the filling time is nothing but it can be written as volume of the mold cavity, that is Vm upon Ag into Vg, which is velocity at the gate. So in simply it can be written as square root of 2g st, and since there is no hc is given, so simply can I say hs itself act as a ht. So from this, if you put these values, so this is 1200, and what about ag? Ag is nothing but this is a2, a2 itself act as a ag, because you can see in the cross section area at the base of the space 2 centimeter, and the horizontal runner is also provided here. So if I assume the diameter of the horizontal runner is same as the diameter of base of the sprue, correct? So simply we can write this is equal to, and if I draw its figure, then it is looking like this, correct? So this is mold cavity whose volume already given here, and that this diameter is actually, this is called as Vg. Sorry, this velocity at this is called as Vg, which is nothing but this is square root of GST. Yes or no? And since the height of the cup is not given, so simply here we assume there is no pouring cup. So instead of HT, here I am writing HS. And similarly, area at this is called as AG. Yes or no? Correct. So if you put these values here, then simply here we get 1200 cc over area is given, that is 2 centimeter, square root of 2g. So we need to write this velocity, this g in centimeters. So by multiplying 100, here we can get 981 centimeter per second square into hs, that is 10 centimeter. So when you simplify this expression, so simply here we get 4.28 second. 4.28 second. Yes or no? Like this, you will get the answer. Okay, so let's see another question. So the figure shows a pouring arrangement. You can see in this, the figure shows Figure shows a pouring arrangement for the casting of metal block. The friction losses are negligible. The acceleration due to gravity is 9.81 meter per second square. The time in second. So you can see this is the casting. So this is pouring basin, and you can see this height is nothing but this is HT. This is equal to 20 centimeter. And the diameter of the sprue, this is cylindrical sprue. So the diameter is uniform throughout the length. So let us assume this diameter is nothing but this is diameter 2 and 3. Correct? Which is same. So from this simply we can get AG, which is equal to pi by 4 d square, or simply you can say pi by 4 into 2 square. So this is cancelled out with this. So the area at the ingate is nothing but this is pi. Correct? And the size of the casting is also given here. So we need to calculate the time in second to fill the mold cavity. So once again you can see, since the molten metal enter into the mold cavity at the top surface, so this is a case of top getting. So here we need to calculate pouring time for top getting. So pouring time of top getting is nothing but it can be written as Vm over Ag into Vg. Yes or no? And the volume is nothing but this is L length into width into height, that is 40 into 15 into 30. This is the volume of the casting over Ag is nothing but this is pi. After simplifying this, here we get pi into what about Vg? Vg is nothing but this is root 2g st. Yes or no? Root 2g st. So simply if I put the direct value on this, so 2 into g is given here, that is 9.81 meter per second square. So obviously here we put all the values in centimeters, so we also need to convert this in centimeter. So it will be written as 981, and the height of the molten metal head, that is 20. So after simplifying this expression, here we get 28.92 second, 28.92 second. Is it clear? So this is the right answer. This is the right answer. So this is a very simple question, so don't worry about this. Okay, let's see another question. The fluidity of the molten metal of cast alloy without any addition of fluxes increases with increasing. So fluidity means ability to flow of the molten metal. Fluidity means ability to flow of molten metal. Correct? And it is obtained by a test which is named as fluidity test. Fluidity test, and especially if I say spiral fluidity test. So in this we have a pattern like this. Correct? And with the help of this pattern, and this is sprue. So this is our pattern. So with the help of this pattern, first we make a mold cavity. Like this. Yes or no? With the help of this pattern, you can make a mold cavity like this. Let's say this is a mold cavity. Correct? And here we have a sprue base, and this for and here we have a sprue base, and this is connected with the sprue base and the sprue. Correct? Now when you pour the molten metal, then this molten metal enters from here. When you pour the molten metal, then this molten metal moves like this, and it fills the mold cavity like this. And according to their fluidity, let's say suppose if this molten metal reaches to this position, so we just measure. Actually in the pattern, the some mark is given here. So once again, after casting, after solidification, once again you put this pattern on this. So from this we can measure how up to what a distance the molten metal can travel. Yes or no? So through this you can find out the fluidity. So this is spiral fluidity test. And now if I see this question, the fluidity of the molten metal of cast alloy without addition of any fluxes increases with increasing. So how to increase fluidity? So fluidity can be increased by freezing range. No, this is wrong answer. Surface tension, this is wrong. Degree of superheat, yes, this is the right answer. By degree of superheat, by increasing the degree of superheat. Degree of superheat means, let us suppose if I draw a cooling curve for the molten metal, then obviously we get this kind of figure. Yes or no? So you can see here, this is the freezing temperature, sorry, this is the pouring temperature, and this is freezing temperature, and this is room temperature. So this is called as degree of superheat. This is called as degree of superheat. So as you add more heat, means higher the degree of superheat, means more heat addition, and therefore the fluidity will be more. Yes or no? Correct? So degree, by increasing degree of superheat, we can increase the fluidity. So the correct answer is option C. The correct answer is option C. Viscosity is also not correct. And obviously when you increase the temperature, then viscosity will decreases. Okay, let's see this question. Match the following sand mold casting defect with their respective causes. Blowhole, misrun, hot tear and versus. So if I talk about blowhole, then it is mainly happens due to entrapment of gas, correct? Or simply you can say poor permeability. If permeability is not poor, then obviously the gases may trapped inside the inside the casting, and when it releases, then they make a hole. Obviously, this is a blowhole is a surface defect. Yes or no? Blowhole is a surface defect. Correct? It will happens like this. This is called blowhole. Correct? So it is mainly caused due to poor permeability. Next, misrun. Misrun is mainly causes due to insufficient fluidity of the molten metal. Misrun means, let's suppose if you want to make a casting like this. If you want to make a casting like this, and now you start pouring from this. So when you pour the molten metal, so before reaching its extreme end, the metal gets solidified. Correct? So this is called as misrun defect. And the reason behind this misrun defect is improper die design, sorry, improper pattern design, improper placement of riser, or simply we can say insufficient fluidity of the molten metal also causes misrun defect. Next, hot tear. So hot tear is nothing but it is a defect produced due to poor collapsibility. Poor collapsibility means, let's say suppose this is a mold cavity, and when you pour the molten metal, then obviously after some times when this molten metal gets solidified, then if there is insufficient collapsibility, means molten metal get stick with the mold wall, and if it doesn't detached while solidification, then the defects may cause. So this is called hot tearing defects. And next one, that is wash defects. So wash defects is mainly caused due to mold erosion. Means, let's say suppose if you make a casting like this is the sprue and this is sprue well. So if you are not directly, if you are not providing sprue well at the bottom, let's say suppose if I remove this sprue well at the bottom, then obviously when sprue well is not here, then very rapidly the molten metal get bent into the mold getting element. Yes or no? So sometimes due to higher turbulency or higher velocity, this corner sand may wash out. Yes or no? So this is called as wash defect. So it mainly happens due to improper design of getting element, along with which we can simply say If the velocity of the molten metal is higher, then turbulency will also higher. And if turbulency is higher, then this kind of defects may happen. Yes or no? So this is called mold erosion. This washing tendency of the sand is called as mold erosion. So this is all about gases. Sorry, this is all about defects. Is that clear? Okay, so the correct answer is P for 3, P for 3, and Q for 4, Q for 4, and R for 1, R for 1, and S for 2. So the correct answer is option A. Correct? So the correct answer is option A. Okay, so let's see another question. In a casting process, a vertical channel through which molten metal flow downward from pouring basin to runner for reaching the mold cavity is, that is called sprue. Correct? So this you can see like this. So this is pouring cup, this is pouring cup, and this is sprue, and this is runner. Is that clear? This is runner. So the correct answer is sprue. Next, you can see for sand casting, steel rectangular plate of size this 80 by 120 by 20 mm. A cylindrical riser has to be designed. The height of the riser is equal to the diameter. You can see this is very important point. The diameter of the riser is equal to height. The total solidification time for the casting is 2 minutes. Solidification time of casting is 2 minutes. Correct? 2 minutes. For solidification time for 3 times in the riser. Sorry, for solidification time of 3 minutes in the riser, the diameter. So yes, the solidification time of riser is also given, which is equal to 3 minutes. So we need to calculate the diameter of the riser. We need to calculate the diameter of the riser. So simply we can say here the solidification time of the casting is given. The solidification time of the casting is given, and this here one thing is also mentioned. Then the solidification time of the riser. So simply if I write solidification time of the casting, which is equal to K times of V by SA whole square. Yes or no? So from this we can calculate K, which is nothing but TSA. Sorry, solidification time of casting over V by SA whole square of the casting. This is casting. Correct? So if I write solidification time of riser, so can I say this is K times V by SA of riser whole square, and this case remains same for both casting and the riser because the metal is remains same. So simply if I put this value, so here we can get TSC, the solidification time of casting, over V by SA whole square of casting into V by SA of riser square. Yes or no? So from this formula, if I put these values, so simply here we get, and you can see the TSR, that is solidification time of riser over the solidification time of casting into V by SA whole square of casting is equal to V by SA of riser whole square. And if I assume this is a top riser, because here it is not mentioning here, so simply we assume this is top riser. So simply can I say, if diameter and height is remain same for the cylindrical riser, so V by SA is nothing but this is the ratio of d by 6 ka whole square. D by 6. Correct? V by SA of cylindrical riser is nothing but this is d by 6 when the diameter and height is remain same. So from this can I say the diameter is nothing but diameter whole square actually. So diameter is nothing but this is 6 times square root of TSR by TSC into V by SA of casting. So now if we put all the values on this expression, so you can say here we get 6 times square root of T by 2 into what is volume of casting. So can I say this is 180, sorry, 80 into 120 into 20 over two times of surface area, that is 80 into 120 plus 120. So simply can I write this expression here? The solidification, sorry, the diameter of the riser is equal to 6 into square root of solidification time of the riser is 3 minutes, solidification time of the casting is 2 minutes into V, that is 80 into 120 into 20 over surface area, that is 2 times of 80 into 120 plus 120 into 20 plus 20 into 80. So when you simplify this expression, then after simplification here we get the diameter of the casting is nothing but this is 51.84 millimeter. So you just calculate. I am not calculating this value. So you just calculate, and after calculation you will get this answer definitely. Correct? So this is the right answer. So like this you can solve any problem related to this. Okay, so let's see another problem. During solidification of pure molten metal, the grains in the casting near the mold wall, you can see near the mold wall we always get fine and ordered grain. Fine and randomly oriented grains, correct? Fine and randomly oriented grains, correct? Because you can see, if I say this is the mold cavity, and when you pour the molten metal inside the mold cavity, then you can see here the metal which is directly connected with the sand wall, due to very huge temperature difference, they can rapidly cool, correct, and they can freeze. यहाँ पे क्या होगा कि ये जैसे कांटेक्ट में आएगा तो टेम्परेचर डिफरेंस बहुत ज़्यादा होगा, एंड बिकॉज ऑफ दिस टेम्परेचर डिफरेंस होने वाला क्या है कि जो मोल्टेन मेटल है वो न्यूक्लियस बनेगा और इमीडिएटली वो सॉलिडिफाई हो जाएगा और वो अपने ग्रुप को लास्ट नहीं कर पाएगा। तो जो जिस पोजीशन में है जहां भी है वहीं एज इट इज सॉलिडिफाई हो जाएगा। तो इसलिए यहाँ पे हम रैंडम ओरिएंटेशन मिलेगा, करेक्ट है। तो फाइन ग्रेन विथ रैंडमली ओरिएंटेड, दिस इज द राइट आंसर। एंड नाउ यू कैन सी a sprue in a sand mold has a top diameter of 20 mm and height 200 mm. The velocity of the molten metal at the a sprue in a sand mold has a top diameter. Sprue top diameter means, let's say suppose if I draw a sprue, then it is looking like this, correct? So this is top diameter which is 1 and this is bottom diameter that is 2. So the sprue in a sand mold has a top diameter, that is D1 is equal to 20 mm, and height is also given here. Height of the sprue is 200 mm. The velocity of the molten metal at the entry of the sprue means velocity at 1, which is equal to 0.5 meter per second. Assuming acceleration due to gravity, that is g, is given 9.8 meter per second square, and neglect losses. If the mold is well ventilated, the velocity up to 3 decimal of the molten metal at the bottom of the sprue is. So simply you can say, if I write the volume flow rate is remain constant. So simply can I say the volume flow rate is nothing but this is A1 V1 is equal to A2 V2, yes or no? So simply here we need to calculate V2. So it is A1 V1 over A2, and V1 is given here, that is 0.5 meter, and what about A1, that is pi by 4 into d square, that is 20 square, over what about A2. So you can see it, a sprue in a sand, yes, this height is given, that is 200 millimeter. So before applying this formula, first we need to write the height of the pouring cup, height of the pouring cup, yes or no. Let's say here we have a pouring cup. The height of the sprue is given, that is 200 mm, but we need to calculate height of the pouring cup. Let's say this is HC. So can I say the velocity at the entry of the sprue, that is V1, is nothing but this is 2GHC. So from this we can calculate HC, which is nothing but this is V1 square over 2C. So V1 is nothing but this is 0.5 meter. So if I multiply with 1000, because in 1 meter we have 1000 millimeter. So this is square over 2G, 2 into G is given here, that is 9.8 meters. So again here I am going to multiply with 1000. So simply here we get, after simplifying this, here we get the height of the pouring cup is nothing but this is, I am directly writing, that is 127.4 millimeter. So let's see if I check once. So height of the pouring cup is nothing but, if I calculate, that is 0.5 into 1000, that is 500 square over 2. Yes, sorry, this is not 127, this is 12.74 millimeter. Correct. So what about total height HT? HT is nothing but this is HS plus HC. Yes or no? HS plus HC. This is 12.74 plus 200. So this is 212. 212.74 millimeter. So if I write this height in meter, so simply here we can get 0. The height is nothing but this is 0.2127 meter. So what about velocity at the bottom? This is V2 is nothing but this is root 2 GST. Directly you can apply. So this is 2G, that is 9.8 into 0.2127. Correct? So once you simplify this, then here we can get 2.043 meter per second. This is the velocity at the bottom of the sprue. So like this you can solve this question. Correct? Okay, so let's see another question. A cylindrical job with diameter 200 mm and height 100 mm is to be cast using modulus method. This is modulus method. So if I talk about modulus method, so this is nothing but the VYSA of casting is equal to 1.2 times 1 VYSA of riser. Actually this is equal to 1.2 times VYSA of casting. Correct? VYSA of casting. So simply you can say this is called VYSA is called modulus. And what is modulus? Modulus is a reciprocal of cooling characteristic, and SA by V is a cooling characteristic. So directly, that's why I am writing directly this relation. Yes or no? And we need to produce a cylindrical job with diameter 200 by 100 mm is to be used. Modulus method. Assume the bottom surface of the cylindrical riser does not contribute as a cooling. It means you have a cylindrical casting like this, and in this cylindrical casting we have a cylindrical riser at the top surface, and if it is top surface, so this surface does not responsible for cooling. So if I say VYSA of riser for this, it is nothing but this is dy5. Yes or no? As a cooling, if the diameter of the riser is equal to height, then the height of the riser is correct, and here the diameter is equal to height is given. So simply if you calculate diameter or height, so simply can I write like this? Equal, is it clear? So you can see here that d by pi is equal to 1.2 times of, and the cylindrical job of diameter 200 mm and height, and the casting is also cylindrical, but its diameter and height is not equal. So simply we can say this is pi by 4 d square into h over this is pi by 4 d square into 2 plus pi dh. Correct? So now if we put this value, and this is diameter of riser and this is diameter of casting. Correct? So the diameter is nothing but this is 5 into 1.2 into, if I put all the values here, the diameter is nothing but this is 200 square into 100 over 5 by 4, 200 square, and obviously here I am multiplying with 2 because we have two surfaces, into pi into 200 into 100, correct? So after simplifying this, here we get, the diameter of the riser is nothing but this is equal to 150 mm, or this is equals to height of the riser. This is equals to the height of the riser. So 150 mm, that is option A is the right choice. Option A is the right choice. So like this, you can solve the problem with the help of this formula, that is a modulus method for riser design. Correct? Modulus method for riser design. Okay, let's see another problem. The part of a getting system which regulates the rate of pouring of molten metal of the riser is. So the correct answer is choke. Choke is nothing but, if I say choke is nothing but, this is the minimum area. It is a minimum area. It is a minimum area. It is a minimum area in the getting element. In the getting element. It is the minimum area in the getting element is called as choke. And the minimum area of the getting element regulates the flow of molten metal. Correct? The flow of molten metal. Is it clear? Okay, so let's see next question. Gray cast iron block of size 100 mm by 50 mm by 10 mm with a central spherical cavity of diameter 4 mm, sand cast. So the shrinkage allowances for the pattern is 3%. The ratio of the volume of pattern to the volume of casting is. So you can see here, shrinkage allowances for the pattern is 3%. Is it clear? Shrinkage allowances is given here, that is 3%. So we need to find out the volume of pattern to the volume of casting. So the volume of pattern to the volume of casting, this is equal to, if I say the shrinkage allowance is given, that is 3% of the pattern. So simply can I say the size of the pattern is 100 into, you can say, first you can say here, if I say here we have a casting, like this. We have a casting like this. Correct? This is a casting. This is a casting. Okay. So this is a casting. So for this, if I draw the pattern size, obviously it is little larger than the actual casting. So this is the casting. This is 100 by 50 by 10. So if I say this is 100, and here the pattern allowance is given, that is 3%, means the pattern size should be enlarged with 3%. So can I say this is 100 plus 100 into 3 by 100? Yes or no? So can I write this is nothing but, if I take 100 as a common, so 1 plus 0.03, or simply you can say 100 into 1.03. This is this length. And similarly, if I write width, so this is 50 into 1.03, and simply if I write height, then this is 10 into 1.03. Yes or no? So this is pattern, and this is casting. Is it clear? And here we need to write the volume of pattern over the volume of casting. which is equal to 100 into 1.03 into 50 into 1.03 into 10 into 1.03 over 100 into 50 into 30, sorry, 10, correct? And when you simplify this, then simply you get this 100 is cancelled out of this, 50 is cancelled out of this, 10 is cancelled out of this. So simply here we get 1.03 whole square. And when you simplify this, then you will get 1.09. This is the answer. 1.09 is the answer. The ratio of volume of pattern to the casting is 1.09. Okay, so let's see this question. This is a very big question, correct? But the answer is very simple. So equal amount of a liquid metal at the same temperature are poured into the three molds made of steel, copper, and aluminium. The shape of the casting is cylinder with 15 mm diameter. The size of the molds are such that the outside temperature of the molds do not increase. Outside temperature of the molds do not increase apparently beyond the atmospheric temperature during solidification. The sequence of the solidification in the mold from the fastest to slowest and the thermal conductivity is given here. For the steel, that is 60.5, for 401 for copper, and 237 watt for aluminum. So obviously, can I say the heat transfer is nothing but this is minus Ka dt by dx. If I write convective transfer, and if I write convective transfer, then this is Ha delta T, Ha delta T, yes or no? So as you see, the temperature of the atmospheric temperature is not significantly changing. Yes or no? So can I say if you have higher conductivity, then higher heat transfer rate takes place. Yes or no? If you have higher conductivity, then higher heat transfer rate takes place. And along with this, you can see also respectively the specific heat of the steel, copper, and aluminum are also given here. Correct? Density is also given here. Correct? So alpha is nothing but this is K by rho Cp. Alpha is nothing but this is K by the alpha is a thermal diffusivity. Alpha is equal to K by rho Cp. Is it clear? Higher the thermal diffusivity, higher will be the heat transfer rate. Yes or no? Is it clear? So you can see here for steel, here we have three metals, that is steel, then copper, then aluminum. So if I write the value of K for steel, then this is 60.5, this is 401, and this is 237 in watt per meter Kelvin. While as the specific heat, if I see, then the specific heat for the steel is 434, 385, and 903. And specific heat means specific heat indicates the heat storing capacity. Higher will be the heat storing, higher will be the rise in temperature. Correct? And if I talk about the density, then this is density is 7854, 8933, and 2700. Yes or no? So these are the values which is given here. So we need to find out. First, you can see equal amount of liquid metal at the same temperature are poured in three molds steel, copper. The shape of the cylindrical this are such that the outside temperature of the mold do not increases apparently beyond the atmospheric temperature. The sequence of solidification, actually we need to find out sequence of solidification, means which metals get solidified first, and then after that which metal gets solidifies. Is that clear? So if I talk about this, and then so you can see here, if you see the K is maximum for Cu, yes or no? If you calculate alpha, then obviously for copper we get maximum value. Correct? For copper we get maximum value because the difference in these values are not very much higher, but the difference in this and this is very much higher. Correct? So can I say the alpha of copper is maximum then the alpha of aluminum, and then the alpha of steel. You just calculate it, correct? So here we get this relation, correct? And once you have this relation, so simplify, we can say here the copper gets solidified faster if alpha is higher. If alpha is higher, the heat transfer rate will also higher, or simply we can say this faster solidification takes place. Faster solidification takes place. Yes or no? So simply can I say the solidification of copper is faster than the aluminum than steel. So correct answer is option C. Correct. Okay, so let's say another question. The ratio of solidification time of the cylindrical casting, where height and radius, height is equal to radius of that of cubical casting of side 2 times the height of cylindrical casting. Correct. So you can see here we have the two casting. One is cylindrical casting and one is the cubical casting. The ratio of solidification time of cylindrical casting over the solidification time of cubical casting. We need to calculate this. Correct. So first the casting, cylindrical casting, the height is equal to radius. The height is equal to radius, means height is lower than the diameter. So this is h and this is d, which is equal to 2 times of h, because in the question it is given here the height is equal to radius. So diameter, obviously we know that diameter is equal to 2 radius. So can I say d is equal to 2h? Yes or no? Correct. And for the cubical casting, the sides 2 times the height of the cylindrical, means this is a, which is equal to 2h. So if I see the solidification time of the cylindrical cylindrical casting over the solidification time of the cubical casting, so this is nothing but simply here we write pi by 4, or if I write in terms of radius, so can I say this is pi r square into h over pi r square into 2 plus 2 pi r into h over a cube. So simply you can write, since r is equal to h, so no need to represent this height in terms of diameter. So simply if I write in terms of radius, correct. So this is 2h, or we can say this is equal to 2 times of r. So this is, you can see this pi is cancelled out with this. So simply here we get and r is equal to h. So can I say this is r cube over 2r square plus 2r square. This is 4 times of r square over 2r whole cube. After simplifying this, this is cancelled out with this. So r by 4 times, and yes, here we also have a square, or sorry, 6a square. So instead of writing this, can I say here we have this is a by 6, and a is nothing but this is 2r by 6. Yes or no? So from this, it can be written as r by 4 over r by 3. So r is also cancelled out. So this is 3 by 4. If we calculate this value, and one more thing, I forget to write this is square. This is square, correct? So can I say this is whole square? So the solidification time of cylindrical riser over solidification time of cubical casting is equal to 9 by 16. Yes or no? 9 by 16. So after calculating, here we get the correct answer is 0.6. Yes, 0.5625 Is it clear? This is the ratio and this is the right answer, correct? So like this you can solve it. So this is very simple question. Okay, let's see another question. The solidification time of casting is proportional to V by A whole square, where V is the volume of the casting and A is the total casting surface area losing heat. Two cubes of same material and size are cast using sand casting process. Two cubes of same material. The top face of one of the cube is completely insulated. Correct, means suppose if you have a cube like this, the size of both the cubes is remain same, but one of the cube is one side of the cube is completely insulated like this. The ratio of the solidification time for the cube with the top face insulated to that of the other. So simply if I say the V by SA of this is nothing but this is A cube times 5 times of A square. Why? Because one surface is insulated. And similarly for this if I write, and let's say this is 1 and this is 2. So this is V by SA of 1, and if I say V by SA of 2, so this is nothing but this is A cube by 6A square. So from this simply here we get V by SA of 1 is 1 by A by 5, and this is V by SA for case 2 is A by 6. So we need to find out the ratio of solidification time for the cube with top face insulated to that of other. So TS of 1 over TS over 2. So this is A by 5 whole square over A by 6 whole square. So can I say this is 6 by 5 whole square, 36 by 25. So after simplifying this, okay, no need to simplify. We need to give this answer in the same way. So the correct answer is option B. This is the right answer. 36 by 25, correct? Okay, let's see another question. In a full mold cavityless casting process, the pattern is used. Full mold. In full mold, we use expandable polystyrene foam. This is the correct answer. The pattern material is polystyrene. Correct. In full mold casting, we use polystyrene foam. So what about this? A cylindrical riser of 6 centimeter diameter and 6 centimeter height has to be designed for a sand casting mold for producing a steel rectangular plate of 7 centimeter by 10 centimeter by 12 centimeter. Having the total solidification time is this. The total solidification time of the riser is correct. So you can see the cylindrical riser whose diameter is 6 centimeter and height is 6. Means this is a case of D is equal to H, which is equal to 6 centimeter. Yes or no? Has to be designed for a sand casting mold producing a steel rectangular plate of this dimension having the total solidification time. And the solidification time of the casting is equal to 1.36. The total solidification time of the riser is. We need to calculate the solidification time of riser is. So can I say the solidification time of the riser over the solidification time of the casting is equal to V by SA whole square of riser over V by SA whole square of casting. Yes or no? So simply from this solidification time of the riser is nothing but this is solidification time of the casting, which is 1.36 into, since this is D is equal to H and if I assume this is top riser, so can I say this is D by 6 over V by SA. So this is 7 into 10 into 2 over 2 times of 7 into 10 plus 10 into 2 plus 2 into 7. Correct? And this is whole square. This is equal to whole square. And instead of diameter, if I put its value, so can I say this is nothing but this is d by 6, that is 6 by 6. So after simplifying this, here we get 3 minutes. After simplifying this, here we get say 3 minutes. So you just calculate. I am not calculating this value. Correct. After a calculation of this, you will get definitely you will get this answer. Okay, so let's see another question. A cylindrical blind riser with diameter of d and height h is placed on the top of the mold cavity of a closed type sand mold as shown in the figure. If the riser of the constant volume, then the ratio of solidification time in the riser is the least when the ratio of h by d is when the ratio of h by d is. So in this case, the height and diameter of the riser is given. So if I say if this is the top riser, so the surface area for the top riser is nothing but this is pi by 4 d square plus pi dh. Correct? And this is for top riser. Correct? For top riser. Is it clear? And in bottom riser we multiply with 2. And what about the volume of riser? This is nothing but this is pi by 4 d square into h. This is the volume of the riser. Is it clear? So from this, can I say the h is nothing but this is 4v over pi d square, and in this one thing is mentioned, the volume is remain constant. The volume is remain constant. So area can also be written in terms of the volume. This is nothing but surface area, that is pi by 4 d square plus pi d into, instead of h here I am writing 4v over pi d square. Yes or no? So this is the surface area. So simply we can say for least the solidification in the riser is the least. For least solidification time, for least solidification time, can I say the surface area, because as you know that from Chvorinov equation, the solidification time is nothing but this is V by SA whole square. Yes or no? For least solidification time, minimum solidification time, the surface area will be maximum. Yes or no? For least solidification time, the surface area becomes maximum. So for maximum surface area, can I say the del SA by del D, which is put it equal to 0. You just differentiate this expression with the help of with respect to diameter, then you will get the answer. So once you differentiate, then simply you can see here we get pi by 4 into 2d plus this is d is cancelled out with this, so here we have 4v, pi is also cancelled out, and if you differentiate d to the power minus 1, so it can be written as d to the power minus 1 minus 1. So this is minus sign. Here we get minus sign, and yes, minus 4v upon d square, and this is equal to 0. Yes or no? So when you simplify this, 4v upon d square. So from this, if you simplify this, so can I write this is 4v over d square is equal to pi by 4 times 2d. Correct? So again, if you multiply with diameter, so here volume becomes this is 2. So pi d cube by 8. Yes or no? Pi d cube by 8. And from this, here we have volume is equal to 4, volume is equal to pi by 4 d square into h. This is equal to pi d cube by 8. Yes or no? So now if you simplify this, then obviously this pi by 4 is cancelled out. Then simply here we get this also is cancelled out. So here we need to find out the ratio of h by d. So simply can I say the h by d is nothing but this is 1 by 2. Correct? So this is the correct answer, 1 by 2. Yes, option 1 by 2. Yes, option A is the right one. So like this you can solve this question. Okay, so let's see another question. The hot tearing in a metal casting is due to high fluidity, high melting temperature, wide range of solidification temperature, low coefficient of thermal expansion. So if I talk about this question, then hot tear means when the thermal stress is induced, in the material, then due to different solidification at different zone, we get hot tier kind of defects. So the correct answer for this is wide range of solidification temperature. Is that clear? Okay, let's see another question. Match the casting defects with group A with the probable cause of group B. So first you can see here we have hot tears, shrinkage, blowhole, cold set. So this very simple is cold set. So cold set defect is mainly caused due to improper fusion of two streams of liquid metal. Yes. So S1, S1. So only these two options. This is cancel out. This is cancel out. Next blowhole. It is due to low permeability. So R2. So R2. R2. Yes. In both the options we have R2. Okay, so next you can see shrinkage, volumetric contraction both in liquid and solid. So this is Q to Q3, Q3. So option B is the right answer. Hot tier differential cooling rate. Hot tier is differential cooling rate. So SRQP 1 2 3 4. So 4 3 2 1. This is the right answer. Okay, so let's say this question: which of the following casting process uses expandable pattern? A pattern which can be melted while casting, yes or no? An expandable mold also. So cell molding, no. Investment casting is the right answer, in which wax is used as a pattern material, and first we make a pattern with the help of injection molding, and after getting mold, after getting pattern, we dip into the slurry, and once the slurry get uh, solidified over the surface of pattern, then you melt the pattern, and after melting you will get the mold cavity, yes or no? So the pattern get expandable, yes or no here? And after getting mold cavity, you just pour the molten metal into the mold cavity. Then after solidification of mold cavity, the mold cavity may also expandable, may destroy for getting the casting. So the correct answer is option B. In sand casting, fluidity of the molten metal increases with increasing degree of superheat. This is the right answer. No need to move in the downward side. Decreasing pouring rate. This is wrong. Increasing thermal conductivity of the mold. This is wrong. Everything is wrong. So correct answer is increasing degree of superheat. Higher the heat, higher will be the fluidity. During the filling process of a given sand mold cavity by molten metal through a horizontal runner of circular cross section, the friction head loss of the molten metal in the runner will increase with. So as you know that friction loss is nothing but this is 4FLV square by 2GD. 2GD, I don't know what is the denominator exactly, but from this simply we can say HF is directly proportional to V square. So increasing the runner diameter, decreasing internal surface roughness of the runner, decreasing length of the runner, increasing average velocity. Yes, increase in the average velocity. As you increase the average velocity, the surface roughness will be increases. Okay, solidification time of a metallic alloy casting is directly proportional to surface area. Solidification time, as you know that from Chvorinov's equation, this is V by SA whole square. So solidification time is directly proportional to volume and inversely proportional to surface area. Directly proportional to surface area, this is wrong answer. Inversely proportional to specific heat of the cast metal, don't know. Increase the proportion of thermal diffusivity of the inversely proportional to thermal diffusivity, wrong answer. Inversely proportional to the pouring temperature, solidification time inversely proportional to pouring temperature. So let's see, if you increase the pouring temperature, then the solidification time will be decreased. This is wrong. This is wrong. This option is also wrong. Is it clear? So the correct answer is inversely proportional to specific heat. You can see from this volume equation, volume indicates heat storage. Yes or no? जो यहाँ वॉल्यूम है वो क्या बताता है? हीट स्टोरेज को. वाइल एज सरफेस एरिया इंडिकेट्स हीट डिसिपेशन, हीट ट्रांसफर रेट को बताएगा. And as you have higher inversely proportional to specific heat, if you have you can say, if I say inversely proportional to specific heat, let's say this is C, specific heat is C. So as you increase the specific heat, the solidification time will be decreases. So lower specific heat means lower heat storage. Correct? Lower specific heat means lower heat storage. जितना हीट स्पेसिफिक कम होगा, कम हीट वो एब्जॉर्ब करेगा, लोअर हीट स्टोरेज, और कम हीट स्टोर होगा तो ऑब्वियसली द सॉलिडिफिकेशन टाइम बिकम्स इंक्रीजेस. So the correct answer is option B. Correct? So are you getting this point? And a solid cylinder of diameter T and height is equal to D, and solid cube of cylinder whose diameter and height is given equal, and solid of cube L are being sand cast using same material. Assuming there is no superheat in both the cases, the ratio of solidification time of cylinder over solidification time of cube is. So can I say V by SA whole square of cylinder over V by SA of cube? And you can see here for cylinder the diameter is equal to height, yes or no, which is equal to D. Is it clear? So if I assume this is a casting, so obviously heat is transferred from each side. So the V by SA of cylinder is nothing but it can be written as D by 6, and similarly V by SA of cube is nothing but this is A by 6, or simply you can say L by 6. Correct? So the solidification time of cylinder over the solidification time of cube, this is equal to capital D by 6 over L by 6 whole square, or simply you can say D by L whole square. So D by L whole square, option D is the right answer. Correct? Okay, so what about this? Hot chamber die casting is not suited for lead and its alloy, zinc and tin and its alloy, aluminum and silver. So hot chamber casting is not suited for aluminum alloy because its melting temperature is more than all these three metals. And hot chamber die casting is mainly used for casting of low melting temperature alloys, and the melting temperature of lead and tin and zinc are very less as compared to other metals. Yes or no? So the correct answer is option D. Is that clear? Okay, let's see another question. In hollow cylindrical parts, you can see here, made by centrifugal casting, the density of the part is max. You can see if you make a casting with centrifugal cast, if you make a hollow cylindrical pipe with centrifugal casting, then you can see here, this is inner radius and this is outer radius, and the centrifugal force is nothing but this is mr omega square. Correct? Mr omega square. So higher the radius, higher will be the centrifugal force, and higher the centrifugal force, higher will be the density. This is the main concept behind this. In hollow cylindrical parts made of centrifugal casting, the density of the part is maximum at the outer region. Yes, it is right. Maximum at the inner region, this is wrong. Maximum at the mid, this is wrong. Uniform throughout, wrong. So the correct answer is option A. The correct answer is option A, because at the maximum, the outer diameter, outer region, we have maximum radius. Next, match the following in group 1 and group 2: sand casting, centrifugal casting, investment casting, and die casting. And here we have application. Correct? So you can see here the sand casting mainly used for making pulleys, large belts. So first we see centrifugal casting. Centrifugal casting is used for if I talk about semi-centrifugal, then it is used for making pulleys. Correct? So for die casting is used for mainly making turbine blades. Sorry, investment casting mainly used for making turbine blades. So R1. So you can see, is there any option? R1 and Q4. R1 and Q4. Yes, we have this option. Correct? And if I talk about die casting, then obviously with the help of die casting we can make IC engine part. So S2. S2, yes, it is right. And sand casting for large well, yes, option 3, yes. So option C is the right answer. Option C is the right answer. Cold set is a defect in a casting due to sand Sand sliding from the no internal voids, no discontinuity, no. Two streams of the material does not fuses properly. Yes, option D is the right answer. Mold set defect means you can see here. Suppose if you have a casting like this and you pour the molten metal from here and you also pour the molten metal from here. So two stream of the molten metals are moving like this. Yes or no? And one molten metal stream is also moving like this. And if both molten metals does not fuses properly, before fusing they get solidified, then this defect is called as cold set defect. This is called as cold set defect. Is it clear? When two streams of the molten metal does not fuses properly, then this is called as cold set defect. So option D is the right answer. Okay, next question. A cast steel slab of dimension 30 by 20 by 5 centimeter is poured horizontally using side riser. You can see here we have side riser. Side riser means all the surfaces are involved for solidification. The riser in a cylindrical in shape with a diameter and height is both are equal. So for side riser, simplify it for side riser. If diameter is equal to height, if diameter is given equal to height, the V by SA of riser is nothing but this is D by 6. Is it clear? The freezing ratio of the mold is, so the freezing ratio means this is X, that is V by SA of casting over V by SA of riser. Correct? This is called freezing ratio. This is called freezing ratio. Yes or no? This is called freezing ratio. So simply if I put these values here, so V by SA of casting, so it can be written as 30 into 20 into 5 over 2 times 30 into 20 plus 20 into 5 plus 30 into 5. So this is V by SA of casting. And similarly, if I write V by SA of riser, so this is D by 6 and the diameter is, what is the diameter? No, this is not given, so let's say this is D by 6. This is D by 6. So now if you simplify this, so let's see. If I talk about the correct answer for this question, so this is 8D by 75. This is 8D by, so you can see here, actually this is not V by, this is a casting by, sorry, this is riser by casting. Actually, the cooling characteristic, you can see the cooling characteristic is nothing but this is SA by V of SA by V, correct? So the modulus is nothing but, this is called as 1 by CC. So simply we can say V by SA, correct? And the freezing ratio is nothing but this is the ratio of modulus of riser over modulus of casting. So this is V by SA of riser over V by SA of casting. So this actually now here I am going to change this. So you just see this term is in denominator actually, not in numerator, and here you will get D by 6. Now it is correct. So after simplifying this relation, so simply here we get this is 8D by 75. 8D by 75. Is it clear? This is the right answer. So the correct answer is option A. Okay, wood floor is added to the core sand to improve collapsibility, die strength, shear strength. So correct answer is collapsibility. Actually, wood floor is, you can say this is a mold cavity or a core. If we put a core and if we add in the wood floor, so obviously when the molten metal is poured, then the by the heat of molten metal, the wood floor may burn out and makes a layer of carbon over the core. And due to this, the collapsibility means detachment of the molten metal from the core may easily takes place, and this ability is called as collapsibility. So detachability of the molten metal from the core material, core sand, is called as collapsibility. or any sand. Correct? Detachability of the molten metal from the sand is called as collapsibility, and by addition of wood floor the collapsibility may improve. Yes or no? Now you can see the getting ratio 1 is to 2 is to 4 is used to design the getting system for magnesium alloy casting. This getting ratio refers to the cross sectional area of the various getting element are given down sprue runner. So you can see if I talk about the getting ratio, so it is always represented by the area of the area of the sprue, area of the sprue. This is area of the sprue to the area of runner, correct, to the area of ingate. This is called as getting ratio. This is called as getting ratio. It is the ratio of area of sprue to the area of runner to the area of ingate. So you can say down sprue is 1, runner is 2, 3. So 1 is to 2 is to 1, 2 and 3. So option A is the right answer. Option A is the right answer. Which of the following is not a property of a sand mold? Permeability, collapsibility, strength, fluidity. And fluidity is the right answer. Fluidity is not the property of molding sand. Permeability, collapsibility and strength is the property of a sand. According to Chvorinov rules, the solidification time of the casting is proportional to V by SA area to the power n. So obviously you can see the solidification time with respect to Chvorinov's equation is nothing but this is V by SA whole square. So here n is equal to 2. This is n. This is n. This is n. So n is equal to 2. So option C is the right answer. Chaplets are placed between the mold in order to. Chaplets actually, when you can see, let's say suppose you have a mold cavity, and in this suppose you have a core like this. If you have a core like this, and this is a mold box in which we have a sand. This is sand and this is core, correct, and this is mold cavity. Sometimes when the core print area is not able to support the core, then obviously we provide a support, yes or no, a metallic support to the core, yes or no, like this. This is the metallic support provided to the core. So this metallic support is called as chaplet. This is called chaplets. Metallic support is called as chaplet. So promote directional solidification, this is wrong. Help allowing the metal, not wrong. Facilitate easy removal of the core, this is wrong. Prevent core movement due to the buoyancy, yes, this is the right answer. When the core print area is not able to resist the buoyancy force, then we need some extra support, and this metallic support is called as chaplet, correct. This metallic support is called as chaplet. Okay, so let's see another question. The primary function of riser is to feed the molten metal to the casting as it solidifies, prevent the atmosphere air contact, galat, allow gases to easily escape, wrong, molten metal, yes. So the correct answer is A. The primary function of the riser is to it act as a reservoir and which provides extra molten metal while casting while solidification of the casting to prevent the liquid and solidification shrinkage. Okay, let's see another question. The optimum pouring time for a casting depends upon several factors. One of the factors among them is location of riser, pouring of sand mold, fluidity of casting, area of the pouring basin. So the correct answer is fluidity of the casting metal. Higher the fluidity, lower will be the pouring time. Is that clear? Next, assertion and reasoning question. Converging passage is used for feeding liquid metal into mold. Inhalation of air promotes blowholes in a casting. Inhalation of air promotes. So converging passes, you can see converging passes. If I talk about converging passes, so you can see here it is nothing but converging passage means if you provide like this. So in this case, obviously the full of the molten runner, the molten metal can move, and since at the entry the opening is very less, so it will provided some back pressure, yes sir. So this is called as pressurized getting system. This is called as pressurized getting system. And whenever we have pressurized getting system, then the obviously the velocity will be increases. Velocity of the fluid will molten material will increases, and as your velocity increases, the turbulence will also increases. Turbulence will also increases. Yes or no? So converging passage used for feeding liquid metal into the mold cavity. This is individually wrong, right? Inherent inhalation of air promotes blowholes in casting. This is also right. So the correct answer is both statements are right, but R is not the correct explanation of A. So option A and R both are true, but R is not correct. So option A is the right answer. For casting of turbine blades made of high temperature and high strength alloy, the most suitable process is investment casting. So whenever you cast very high melting temperature alloys, then we always use investment casting process. Correct? What is the velocity of the steel at the bottom of the sprue? What is the velocity of the steel? What is the velocity of the steel at the bottom of the sprue? What is the velocity of the steel at the bottom of the sprue? If the sprue height is 30 centimeter, assuming the friction and other losses is 20%. So velocity is nothing but, let's say first you calculate root 2 GST, and if you have 20% losses, so you just multiply with 0.8. So velocity is nothing but this is 2 into G, that is 9.8, and into and obviously this is in centimeter, or you just write in 0.3 into 0.8. So after calculating this, you will get the final velocity of the molten metal. So if I say this is nothing but 2 into 9.8 into 0.3 into 0.8, so this is square root of this. So here we get this is 2.1688 meter per second. This is the velocity at the bottom of the sprue. Okay, so next you can say green strength in powder metallurgy refers to the strength of origin material. Green strength means when you compact the material, when you compact the metal powder, then you will get the final product, then you will get the product which is called as green product. Original material in the bulk form, the powder before compaction, the powder after compaction, the powder after centering and cooling. So original material in the bulk, so the powder after compaction. Option C is the right answer. Okay, let's see. For the same material, powder metallurgy process is superior to casting for making large product, for better control over the density of the product, better strength of the finished product, making part with wide variation of thickness at a different section. Correct? So the correct answer for this question is better control over the density of the product. If I see, the correct answer for this question is, so the correct answer is making large product. This is wrong answer because powder material is mainly used for making small size product. Better control over the density of product. So obviously the control of density is very difficult in the powder metallurgy. Better strength of the finished product. This is also not good. Making parts with wide variation of the thickness at a different section. Yes, this option is possible with the help of this. The process by which cell-like casting, like toys, are made is, so this is mainly use cell-like casting. So sludge casting is used. Negative allowance is provided on the pattern to take care of draft allowance. Negative allowance is only provided for the shaking allowance, because when you shake them, let's say suppose if you have mold, this is top view, correct, and this is mold cavity, mold box, and this is a pattern. Correct? This is a pattern. This is a pattern. Is it clear? Pattern. And obviously, when you perform ramming action, then due to ramming action, what will happen? Some of the sand may stick on the surface of the pattern. Yes or no? So first we need to make break this contact between the pattern and the sand. So for this, we just shake it along this direction, parallel to the parting plane. Yes or no? So due to shaking, what will happen? So the size of the mold cavity slightly increases. To compensate this, we need to provide pattern to be negative allowance? Yes or no? So the correct answer is second allowance. Green sand mold indicates that polymeric sand mold has been totally dried. Mold is green in color. Moisture containing sand is called as green sand. Is it clear? Two streams of liquid metal which are not hot enough to fuse properly. This is cold set defect, and many times I already told you. Which of the following engineering metal is most suitable candidate for the hot chamber die casting? And obviously in a hot chamber die casting, low melting temperature alloys can be cast. So the correct answer is tin. Its melting temperature is around 327 degrees centigrade, which is lower than all the remaining metals. Gray cast iron block of this are made cast in a mold. Shrinkage allowance are provided to the pattern. 1% the ratio volume of the pattern to the volume of the casting is. So obviously the size of the pattern is nothing but this is 200 into 1.01 into 100 into 1.01 into 10 into 1.01 over 200 into 100 into 10. And when you simplify this, then definitely you will get 1.01 whole cube, and this answer is 1.03. So 1.03. And let's say how you write this dimension. So let's say this is your casting. Is it clear? This is your casting whose size is given, that is 200 by 100 by 10. So for this you need to make a pattern. Yes or no, like this you need to make a pattern. So the size of the pattern, 1% allowance is given here. So can I say this is 100 into 1 upon 100. So here we can get 100 if I take common. So this is 1.01. And why I am writing this? We need to enlarge the pattern. So how much enlargement is required? 1%. 1% of what? 1% of total dimension. So 100 into 1 by 100. Correct. Similarly, can I say this is sorry, this is 200, not 100. Correct. And this is similarly for 100 you can write 100 into 1.01, and this is 10 into 1.01. Correct. So this is pattern and this is casting. Correct. So by putting those values on this expression, then you will get the answer. So option D is the right answer. Okay. So hardness of the green sand mold increases with increase in moisture content beyond 6%, increase in permeability. Hardness in decrease in permeability, increase in both moisture content and permeability. So listen, the hardness of the mold sand increases in the increase in moisture content beyond 6%. This is wrong answer. Decrease in the permeability is the right answer. Decrease in permeability means decrease in the space between the, let's say this is if these are the sand particles, then obviously this vacant space is called as permeability. Void. So if you reduce the voids, then the hardness, this is voids, and if you reduce the voids, then obviously the hardness will be increases. The hardness will be increases. Yes or no? So the correct answer is option C. The primary purpose of sprue in a casting mold is to feed the casting at a rate consistent with the rate of solidification, act as a reservoir of molten metal. Yes, so the correct answer is option B. It acts as a reservoir for the molten metal. Next, shrinkage allowance on the pattern is provided to compensate for shrinkages when the temperature of liquid metal drops from pouring to freezing temperature. The metal charges from liquid to solid state. Sorry, metal changes from liquid to solid state. Temperature of solid phase drops from freezing to room temperature. The temperature of the drops from pouring temperature to room temperature. So shrinkage allowance on pattern. So pattern can compensate solid shrinkage only. You can see here. If I draw the cooling curve for the metal, this is temperature and this is time. So the temperature corresponding to this is pouring, this is freezing, and this is room temperature. Is it clear? So first this is called liquid shrinkage. And this is solidification shrinkage. This is solidification shrinkage. So first two types of shrinkages are compensated by riser design, and this is called solid shrinkage. And this is compensated by pattern design. This is compensated by pattern design. Yes or no? So option C is the right answer. Light impurities in the molten metal are prevented from reaching the mold cavity by providing strainer, skim bob, bottom well, All of the above. So the correct answer is mold cavity. So the correct answer is option D. All these things are provided to collect lighter as well as heavier impurities in the molten metal. Centrifugal casting products have large grain structure with high porosity, fine grain structure with high density. Yes, fine grain structure with high density. Because due to centrifugal action, the density of the metal will increases. And since here we use metallic mold cavity, then obviously the heat transfer rate is also very fast. And due to this, the fine grain and dense structure will obtain. When there is no rise room temperature changes, the total shrinkages allowances on a pattern is independent of pouring temperature of the liquid metal, freezing temperature of the liquid metal, the component size, the coefficient of thermal contraction of solid metal. When there is no room temperature change, the total shrinkage allowance on the pattern. If I talk about in the pattern, so it doesn't depends upon pouring temperature, and it is independent of pouring temperature. It only depends upon the coefficient of thermal. You can see for pattern simply we can write this is L alpha delta T. And what is delta T? L alpha delta T is nothing but this is freezing temperature minus room temperature. Yes or no? So it depends upon the size of the casting, it depends upon the coefficient of thermal expansion, and it depends upon the freezing and room temperature. So this is wrong answer, this is wrong answer, and this is wrong answer. So correct answer, independent of pouring temperature. So option A is the right answer. In a green sand molding process, uniform ramming leads to less chance of gas porosity, uniform flow of molten metal into mold cavity, greater dimensional stability, lessen expansion type cast, greater dimension stability of the casting. When you ram properly, then obviously the better hardness and permeability you will get, and better dimensional stability we can get. Converging passage is used for feeding the liquid metal into the mold to increase the rate of feeding. Quick break of the protruding portion of the casting, decrease waste of cast metal, avoid air respiration. So yes, when you use converging passage, then the air respiration effect will also avoided, and increase the rate. And yes, feed rate will not be increased. Okay, the pressure at the in-gate will maximum with the getting range system. In-gate pressure you get maximum when you have getting system. You can say this is 8 is to 3, 3 is to 3, 2 is to 1. So in these cases, in this case we have a riser like this. In this case we have a riser like this. Correct? And in this case we have, sorry, runner like this. And in this case we have runner like this. So the pressure will get maximum in which case? So the correct answer is option C. Correct? So odd one out type you can get the answer. The contraction allowance provided on the pattern and core box compensate for the following type of allowance for provided to the pattern. So obviously solid contraction. Option D is the right answer. Correct? Option D is the right answer. So this is all about question belongs to metal casting process in the GATE exam.